Welcome to our tutorial on leveraging artificial intelligence to enhance your real-time strategy games. Today, we'll explore the different components necessary to implement AI in an RTS setting, boosting gameplay and player experience. In this episode, we'll cover the basics of AI in games, including algorithms, decision-making, and pathfinding techniques. We'll also discuss how to integrate these concepts into Java, showcasing practical examples. One of the fundamental aspects of AI in RTS games is decision-making. We'll dive into an algorithm called Minimax, which is widely used in game theory and can be useful for strategic decision-making. Let's start with implementing the Minimax algorithm in Java. This algorithm explores all possible moves in a game and chooses the best one based on the potential outcomes. First, we need a basic structure for our game state. Next, we'll need a method to evaluate the board and provide a score based on the current player's advantages. This evaluation function is essential for the Minimax algorithm as it guides the AI's decision-making. Now, let's implement the Minimax algorithm itself. We'll create a recursive method that simulates all possible moves and evaluates the outcomes, returning the best move for the AI. With our Minimax implementation ready, we'll incorporate this into our game loop. The AI will decide its move based on the algorithm, allowing for a challenging gameplay experience. Next, let's talk about pathfinding, which is crucial in RTS games for moving units around the map effectively. A popular pathfinding algorithm is A*, which finds the shortest path from point A to point B. We'll implement the A** algorithm in a separate class. This involves maintaining a priority queue to explore nodes based on their costs, while preventing cycles in our path. We've set up our pathfinding function. The AI can use this to navigate the game world efficiently, reacting to player movements and positioning for strategic advantage. Now that we have decision-making and pathfinding in place, let's pair them to allow the AI to engage in combat and resource management, common elements in RTS games. The AI will need to manage resources while simultaneously planning its attacks. In this method, the AI checks its current resources against the cost of deploying troops. If it has enough resources and determines that it is time to attack, it will execute the AI make move function we defined earlier. It's essential to set up the conditions for when the AI should attack. Such sophisticated decision-making leads to dynamic gameplay. Let's build our should attack method now. This method will check if the enemy is within attack range and confirm that the current AI player is not the enemy itself, ensuring that the AI behaves logically. Next, we will implement a visual representation to observe our AI in action. This can be achieved using JavaFX or any graphical library of your choice. In this example, we will use JavaFX for simplicity. In this code snippet, we've created a simple JavaFX application that initializes a window and adds an AI unit represented by a blue square. You can expand on this by adding visuals for the player units, resources, and a map grid. Now we'll connect our game logic with the graphical representation, updating the game view as the AI makes decisions. We'll want to redraw the game state each time the AI takes an action. This method clears the previous state and redraws the game units, ensuring that our visual representation stays in sync with the internal game logic. As we integrate these systems, we need to continuously test and tweak our AI logic. Fine-tuning the evaluation function, pathfinding parameters, and resource algorithms will lead to a more believable and challenging AI. Let's discuss more advanced AI techniques such as behavior trees and finite state machines. These methods provide a flexible and modular way to manage more complex behaviors. A finite state machine comprises various states, e.g., idle, attacking, and transitions based on events. We can implement this by creating a class that manages the state of the AI. In this state machine, we update the current state, execute its logic, and determine transitions to other states when necessary, helping us manage complex AI behavior more efficiently. On the other hand, behavior trees break down behaviors into tasks and decisions, offering clearer control over execution flow. This can allow the AI to make more nuanced decisions. In this example, the behavior tree has a root node that represents all tasks. Each tick updates the state, allowing for asynchronous behavior, a powerful advantage in RTS games. Implementing both FSMs and behavior trees can bring varying levels of complexity to your game. Depending on your goals, you might prefer one over the other, or even a combination of both. Before we conclude, let's quickly recap the main concepts discussed today. We covered the implementation of the Minimax algorithm for strategic decision-making, A*4 pathfinding, visual integration with JavaFX, and more advanced AI methods. AI in RTS games can significantly improve player experience by providing a challenging opponent. Keep in mind there's always room for improvement, so continuously test your AI to ensure it adapts well to player strategies. Thank you for watching this comprehensive guide on using AI in real-time strategy games. Be sure to check out our additional resources for more in-depth insights and practical examples. Don't forget to like, subscribe, and hit the bell icon for notifications on our future tutorials. Happy coding!